All right, so when we talk about things that are concave up, mathematically, they have a positive second derivative. And when we talk about things that are concave down, they have a negative second derivative. And so knowing about the second derivative is something that's going to be helpful to us in identifying maxes and mins and identifying points of inflection. So let me start with an example that we know, we know the shape of. Okay, we're just going to start with that. So let's start with sine. All right, we know the shape of sine, but it's helpful to start with something that's familiar to us before we move to unfamiliar graphs. Let's examine both the first and the second derivatives. So the first derivative of sine is clearly cosine. When we set that equal to 0, we'll get critical points. And those critical points are going to be pi halves and 3 pi halves within the first cycle. We could have 5 pi halves. We could keep going. There's lots of critical points. The second derivative will be negative sine of x when I set that equal to 0. So you're going to do the same thing to the second derivative that you were doing to the first derivative. You should also consider undefined, but I already knew that sine and cosine were never undefined, so I sort of skipped over that section. But we're going to have critical points here. And the critical points for that are going to be 0 pi, 1 pi, 2 pi, etc.
Can we call this?
Not yet. All right, very good. Can you call them inflection points right away? No, just like I don't call them maxes and mins right away. They are critical points and critical points only. The only way they classify and they change from a critical point to a max or min is if I actually see a change on the chart from positive to negative. The same thing is true about the critical points for the second derivative. The only way they classify as an inflection point is if in the second derivative I'm going to see the chart change. Okay, you have to check a chart. You can't just assume, just like I wouldn't assume it was a max or a min without checking a chart, I can't assume it's a point of inflection without checking the chart. So what I like to do is, rather than making 2 charts, I like to make 1 chart and combine everything at the same time. So if I look at all my critical points, I'm going to combine and I'm going to go from 0 pi to pi over 2. So I'm taking the critical points of the second derivative and first derivative all together. And then I'm going to go from pi halves up to pi. So again, that's a critical point from the first and a critical point from the second. Then I'll go from pi up to 3 pi halves. I think I'm going to run out of room. I think I'll stop at 2 pi. And then I'll go from 3 pi over 2 up to 2 pi.
How does that help?
I'm going to show you. Hang on. Let's see if it helps, okay? I'm going to extend my chart now. And I'm going to be looking at both values in the first and the second derivative. So I'll be looking at first and I'll be looking at second at the same time. So I will be picking values in between those intervals. I'll probably pick the fourths because those are, excuse me, those are convenient values. So I probably will pick pi fourths for this one and 3 pi fourths, 5, and 7. And I will be checking both the first and the second derivative values at the same time. So let's check pi fourths, and let's check it in the first derivative, and let's check it in the second derivative. Right, when I check pi fourths in the first derivative and I plug in cosine of pi fourths, remember I'm looking at the first derivative here. Okay, that's going to give me a positive number. And when I check it in the second derivative, what does it give me? A negative number. What does that tell me about that shaped section of the graph? What does the positive part tell me?
It's
increasing, but the negative part tells me that it has a negative curve to it, a negative concavity. All right, so that's this kind of a shape. That's that sort of a section. If I check 3 pi-4 and I put that into both the first and the second derivatives, I'm going to get negative, positive. That tells me that the next section of the graph switches to decreasing, and it has, whoops, it's not negative, negative, is it? It's negative. It's not negative, positive, it's negative, negative. Erase. There we go. Negative, negative. That tells me that the graph is going down and it has a negative pole to the concavity, so it's going to look like that. The next shape of the graph, I plug 5 pi-4 in, I get negative and I get positive when I plug 5 pi-4 in. That tells me the shape of that graph is going to be going down with a positive shape to it, positive concavity shape. And then the last one turns out to be positive, positive, which is going to switch to going up with a positive concavity. And if we put all those pieces together, yes, of course, that does look like a sine curve to me. All right, if I blend all of that together, and let's see, if I connect all of that, for sure, that looks like a sine curve to me. All right, and then I'm looking for identifying maxes or mins. Maxes or mins go along the first row wherever you're having positive or negative changes. So I have a max here, and then another change, which would be a min here. And then the inflection point goes along the bottom row wherever you would have a change in the second derivative, and that only changes once. And so I'm going to have an inflection point right there, okay, at pi, which matches what we know about what sine looks like. So we've just done one on a graph that we actually know what it looks like. Okay? So what we want to do now is move to a graph where we don't necessarily know what it looks like and see what we can do with that. Do you guys have any questions so far? All right, let's try a second one. Let's do the following. Let's do the function where e is equal to negative x squared. Now, I don't know about you, but you probably, maybe you have a perfect picture in your head and you know what e to the negative x squared looks like, but maybe not. So we want to look at the first derivative, and we want to look at the second derivative. The first derivative, e to the negative x squared, will be e to the negative x squared times the natural log of e times the value of negative 2x. Finding the critical points on that would be setting it equal to both 0 and undefined. The only critical point that would come out of that would be 0. All right, the second derivative. What rule do I need to find the second derivative? I have to use a product rule. So I'm going to have e to the negative x squared times the product rule, so negative 2, plus negative 2x times e to the negative x squared times ln e times negative 2x. And I need to simplify and clean that up. So I'll have... Oh, got it, got it. Okay, so then we're going to simplify this to be negative 2 e to the negative x squared, and then I'm going to have plus 4x squared e to the negative x squared, and I want to factor that out. So I'm going to pull out negative 2 e to the negative x squared, and when I factor that, that leaves me with, no, I'll pull out positive 2, I think I don't need a negative. And when I pull that out, I'll have negative 1 plus 2 e to the negative 2x squared. I'm going to set that equal to 0 and undefined, and I'll get critical points from that. when I set that equal to my critical points, I'm going to get plus or minus the square root of 1/2. So I now have 3 total critical points, a critical point that was produced from the original derivative and 2 critical points produced from the second derivative. So now I'm going to set up a combination chart to check the maxes and mins and points of inflection kind of all at the same time. So I'm going to go from negative infinity up to the negative square root of 1/2. I'll go from the negative square root of 1/2 up to 0. I'll go from 0 up to the positive square root of 1/2, and then the positive square root of 1/2 up to infinity. And I want to check both the first and the second derivative at the same time. So I will be pulling values, okay, picking sample values from each region. So, I mean, you can sort of be as crazy with those as you want, but like -5, maybe -0.1, maybe +0.1, and maybe 5, or something like that. It doesn't really matter. I'm going to pause the recording a minute. All right, now that we have the values, we should be able to interpret what's going on at these values. All right, so let's look at just the first row. I've got a plus, plus, minus, minus. What does that mean? Okay, the first row, the first derivative, what does it mean? Plus, plus, minus, minus. Okay, so we're going to have a max here. I'm not going to worry about the stationary points quite yet. I'll come back to that. All right, what about the bottom row where it's plus, minus, minus, plus? I haven't. Okay, so what you used to call stationary points, you now know are going to be inflection points. Okay, but we didn't know that because we didn't know about the second derivative yet. All right, so we have, I shouldn't have pluralized it, inflection point and point. So we have one max that we can defend. You should be able to create and construct a complete sentence. Okay, a complete sentence would read something like this. There is a max at 0, 1 because the values of f prime are changing from positive to negative. So in other words, you should be able to put it into English as well. Okay? On the AP exam, if you only have a chart and you do not have a sentence, you'll get 0 points. Okay? The chart is worth nothing. The chart is really only just your scratch work to help you construct. And every problem in the AP will say, oh, unless it's a multiple choice. If it's multiple choice, of course, just do the chart and then pick your answer. But on the free response, it'll say, find the maxes or mins, period, justify your answer. Which means they want to know a because statement of why it is what it is. So that's one way to say it. You could say the values are changing from positive to negative. All right. You could also say an alternate way of saying the same thing. So here's one option. You could also say because the function f of x changes from increasing to decreasing. That would be a secondary way of saying it. Both are valid, both are worth full credit, full points. Okay, because so ... that can be either one of those answers. So either you're talking about what the derivative is doing, or you're talking about what the original function is doing because you know what the derivative is doing. Once you know what the derivative is doing, if you know the derivative is changing from positive to negative, then the original function was changing from increasing to decreasing. Either one of those is fine. And you'd have a similar statement for the point of inflection. There are points of inflection at such as at negative square root 1/2 and positive square root 1/2 because the values of the second derivative are changing from positive to negative and negative to positive. Or you can say because the original f of x function is changing concavity at those places. So being able to construct good sentences. When we come over Thanksgiving break, you're going to work on constructing good sentences and turning those in. Okay, last set of examples. These are fun. Draw a function of your own. And then given the following constraints. So with the following. A, an even function. B, zero, 2 is a point. Okay, C, 0 to 1. Oops, 1 to 2. 2 to 3. And you're going to be given chart values. And it would be minus plus, minus minus, plus minus. All right, so these are kind of fun. You got to draw your own. All of that should be true. Okay, you have to draw your own. All of that should be true. Okay. Well, if we're going to create a graph, we know that 0, 2 is a point. So let's for sure get that on there. So 0, 2. And then I've got information telling me what's going on from 0 to 1, and 1 to 2, and 2 to 3. Okay, what's going on? What kind of a shape do I draw between 0 and 1, according to the plus minus? Negative slope, so it's going down, and then concave up. All right, so as I draw that, it's going to look something like that. It's going down, but it has concave up shape. Okay, from 1 to 2. What do I need to do? I need to keep going down, decreasing with it. Okay, so I need to show a change. Okay, if you need to like make yourself little pieces of these and like stick them together and to figure out, all right, I had something that was, looking like this connected to something that's looking like this. All right, if you need to do that, you can try that out. All right, and then what do I need to do? Ooh, this is interesting. All right, so if I've got a double negative connecting to something that's going up but also has negative concavity, I just made a cusp. Okay, I just made a cusp. Something like that. Okay, everybody's might look a little different, and that would be fine. What was the point of part A? An even function means the symmetry of one side is exactly symmetric to the symmetry of the other. And so once you've created the space from 0 to 3, you should be also able to create the graph going backwards from 0 to negative 3. And so the fact that it's even means I'll have this connected to that, and I'll have the other side as well. So I actually just doubled the shape of my graph. Okay. All right. Thing. Do you have to do a chart every time? Is there a way to find maxes and mins without a chart and without your calculator? All right, so find maxes and mins without a chart for the following function. 2x cubed minus 14x squared plus 22x plus 5. And the answer is, of course there is. For sure, there's a way to find it. All right, I'm going to need the first and the second derivative though, but I'm not going to make a chart from them. Okay, my first derivative, 6x squared minus 28x plus 22. Second derivative, 12x minus 28. I still need to find the critical points of the first derivative, but I don't need to make a chart to finish. This would be another way, an alternate way of finding max or mins. So if I were to factor that, I would probably take a 2 out of everything. Okay, that's going to leave me with 3x squared minus 14x plus 11. And then I'd want to set that equal to 0 if I could. Probably going to work on factoring that. Okay, a 33 and a negative 14, if I could figure out a way that that would factor. Okay, does that work? Doesn't? How about negative 3 and negative 11? Okay, that factors. So I can factor this into two factors using, I'm going to have 3x minus 11 and x minus 1. Yep, that factors. So my critical points are 1 and 11/3. Now, I can tell if these are going to be max and mins without making a chart because, let me show you some pictures. What do you have here? Max or a min? Max, but what's the same about both pieces of paper? Okay, maxes sit on top of a concave down section. Mins sit in a concave up section. So all I need to know is what the concavity is here to know if it's sitting. I already know it's sitting on one of those two places. So check the double prime for 1 and check the double prime for 11/3. It's pretty easy to plug in the double prime for 1. What do you get?
Negative.
I don't care. I don't care. I don't care if it's, I don't care negative what. I just care that it's negative. So if the concavity is negative, then what is 1 sitting on? A max or a min? Okay, if the concavity is negative, then it's sitting on a max. What about 11/3? If I plug that in, what do I get? I get a positive number if I plug that in, which means I have positive concavity, which means I'm sitting on a minimum. All right, so this is going to be this shape, this one. So I have a max and a min based on the concavity. So I didn't need to make a chart, I just had to think about its concavity to do that.